Okay, we stop at Stefan-Boltzmann's law. A star's luminosity depends on two factors: its surface temperature, its radius. Two things: surface temperature, radius. The relationship between these is known as Stefan-Boltzmann's law, which states total energy emitted by a black body per unit area per second is proportional to the fourth power of absolute temperature of the body. Right? We stay in words, then we write in mathematical form. The relationship between these is known as Stefan-Boltzmann's law, which states that it is equal to, it's given in the formula sheet, L luminosity equals to 4 pi r square sigma t to the power 4, where L is luminosity, R is radius of the star. Right? Remember, radius of the star, not distance. Sigma has a constant value given in the formula sheet. It's called Stefan-Boltzmann's constant. T is absolute temperature. Right? Careful when you write it in this form. Right? This form, F tends to, we think, to take the distance from Earth to the star. But this is radius, right? Not distance. Radius of the star. Okay, and summary, radiant flux intensity is L 4 pi d square. D is the distance between star and Earth. Then Wien's displacement law, peak wavelength, right? Wavelength at maximum intensity or maximum rate of emission is inversely proportional to surface temperature. Usually you don't need to remember. They will give you the value if you need to use it, but usually you don't need to remember this value only Wien displacement law, right? And Stefan-Boltzmann's law. Okay, try this question. Betelgeuse is our nearest red giant star. It has a luminosity of 4.49 × 10 to the power 31 watt and emits radiation with a peak wavelength of 850 nanometer. Calculate the ratio of radius of RB to radius of the sun, RS. Radius of the sun is given. Right? If they require you, then they will have to give you this value, the constant. Okay, the constant. Take lambda max down, then convert everything to SI unit. 2.9 × 10 to the power minus 3. Lambda max. Change it to SI unit. Calculate out. And use the luminosity formula. Stefan-Boltzmann's formula. Right? Subject R is a radius, not distance. Radius. Sometimes we use capital R, sometimes we use small r. Doesn't matter. It's just a variable only. But know that what does it mean? Right? Radius of Betelgeuse. Put in your value, L, that is your L. Is in what? 4 pi sigma. Look into the formula sheet. T is the value. Okay. So we want to find the ratio, calculate the ratio of radius of RB to RS. RB to RS. Right? Three significant figure. Okay, can get the answer.
Yeah.
Okay. Okay, let's summarize for us what you need to know. Right? Standard candle, Wien's displacement law, radiant flux, intensity F, luminosity, what is a black body radiation, Stefan-Boltzmann law. So our last part is Hubble's law and the Big Bang theory. Right, there's the syllabus. There's the Van Hofer line. Right? We thought that the line, we will see a continuous spectrum from the sun. Right? But when we analyze the spectrum, we see dark lines there. Right? This last dark line because of elements present in the sun. So as a continuous spectrum pass through these elements which are in gaseous form, they are absorbed. Right? Yeah, certain wavelength is absorbed. So we can identify them, what element it is. That's the thing we can do. Even the star also, we will see a similar style of spectrum. Okay, emission spectra. Astronomers are very limited in how they can investigate objects in space. All of the techniques used involve analyzing the light emitted from the star or galaxy. Right? We can only analyze the light emitted from the star or galaxy. Right? We cannot go to the star or go to the galaxy. One of the techniques involves analyzing emission and absorption spectra of stars. Elements in the star, predominantly hydrogen and helium, absorb some of the emitted wavelength. That's why we know hydrogen and helium are present in the star. Therefore, characteristic lines are present when spectrum analyzed. Right? Each each element, hydrogen or helium, they have a specific emission spectrum or absorption spectrum. So that's how we can identify the element present in the star or in the sun. Okay, that is emission spectra. Hydrogen measured in laboratory. Right? This part is the blue wavelength. This part is the red wavelength. Remember, they are acting at the longer wavelength. They are wider apart. They are closer apart, the shorter wavelength, which is the blue side lah. Right? This one we measure in laboratory. Right? Top emission spectra shows spectral lines of hydrogen measured on Earth or in laboratory. Right? And this one we measure from galaxy. Shifted hydrogen measured from distant galaxy. Right? The second one is bottom emission spectra shows the shifted line. Right? The lines are shifted to longer wavelength. Measured from distant galaxy. Right? This one measured on Earth. This one measured from galaxy. We see that it's shifted to the red end. That's why it's called redshift. When astronomers observe light from distant galaxies, they observe differences in spectral lines to light from the sun. The lines have the same characteristic pattern, meaning the element can still be easily identified. They just appear to be shifted slightly. The lines in the spectra from distant galaxy show an increase in wavelength. The lines are moved or shifted towards the red end of the spectrum. Recall the Doppler's effect is defined as apparent change in wavelength or frequency of radiation from the source due to relative motion away from or towards the observer. Right? Either the source or the observer is moving. then there's a apparent change in wavelength or frequency of radiation or sound waves. Right? That is your AS work. On Earth, the Doppler effect of sound can be easily observed when sound waves move past an observer at a notable speed, right? A known speed. In space, Doppler effect of light can be observed when spectra of distant stars and galaxies are observed. This is known as redshift if the object is moving away from the Earth, or blue shift if the object is moving towards the Earth. Right? Memorize what is redshift. Redshift occurs when wavelength of spectral lines is greater than the known value due to movement of star away from the observer. The star is moving away from the observer. So it's shifted. Right? The spectral line is greater than the known value. Right? Shifted to the red side. The fractional increase in wavelength or decrease in frequency due to the source and observer receding from each other. Right? Non-relativistic galaxies, Doppler shift can be calculated using this one. That means the speed must be not close to the speed of light. Then we can use a non-relativistic for galaxy, Doppler redshift. Right? This is also given in formula sheet. For non-relativistic galaxy, Doppler redshift can be calculated using this formula, where delta lambda is shift in wavelength. Lambda is the wavelength emitted from the source. Right? Emitted from the source, not the original wavelength. Same, delta F is the shift in frequency. F is the frequency emitted from the source, right? The moving source. V is the speed of recession of the galaxy. C is the speed in vacuum. Cosmologists are able to determine that light from distant star has undergone redshift by examining the line in the spectrum of light from star and comparing with known spectrum. Right? As we have shown there, you can try this question. That one is a source measure on Earth. You can measure from distant galaxy. The spectral line below show dark absorption lines against the continuous visible spectrum. Particular line in the spectrum of light for the source in the laboratory has a frequency of 4.570 times 10 to the power 14 Hertz. Right? This one they are given in frequency, but we can recognize it is longer wavelength. The same line in the spectrum of light from a distant galaxy has a frequency of 4.547 times 10 to the 14 Hertz. What is the speed? What speed is a distant galaxy moving in relation to the Earth? Is it moving towards or away from the Earth? Right? We can study the graph, the spectrum, and see that it's shifted towards longer wavelength. Right? So it's moving away from the Earth. Right? Rather than look at the blue shift, we look at the red shift. Right? Blue shift is on this side. So we take this formula from the formula sheet, put in our value, 4.5 times 10 to the power 0, 4.547, subtract times 10 to the power 14, divide by 4.57 and 10 to the power 3. Right? Take the speed of light across there. So we calculate 1.51 times 10 to the power 6 meter per second. Observer frequency is less than the limited frequency of light from the laboratory source. Therefore, the source is receding or moving away from the Earth at 1.5 times 10 to the power 6 meters per second. Any comment?
No.
Okay, that's an example. Okay, expansion universe. After the discovery of Doppler redshift, astronomers began to realize that almost all the galaxies in the universe are receding. Right? Not one galaxy. Almost all the galaxies in the universe are receding. It means they are moving away from the Earth. This led to the idea that the space between the Earth and the galaxies must be expanding. Right? Space is expanding. This expansion stretches out light waves as they travel through space, shifting them towards the red end of the spectrum. Right? So the space is expanding, so light wave is stretched out to longer wavelength. That explains the redshift. The more redshift the light from the galaxy is, the faster the galaxy is moving away from the Earth. Right? This is an example of a balloon. Right? Balloon dot represent the galaxy lah. So when you blow it, there's an increase in volume, right? Representing the universe are expanding. Right? Space is expanding, not the galaxy moving away. Expansion of the universe can be compared to dots on an inflating balloon. As the balloon is inflated, the dots all move away from each other. In the same way as the rubber stretches when the balloon is inflated, space itself is stretching out between galaxies. Just like dots, the galaxies move away from each other. However, they themselves do not move. Right? It's not the galaxy that moves, it's the space that's expanding. Hubble's law and the Big Bang theory. Edwin Hubble investigated the light spectra emitted from a large number of galaxies. He used redshift data to determine the recession velocity of this galaxy and the standard candle to determine the distance. From the measurement, he formulated the relationship known as Hubble's law. Hubble's law, memorize it, states that recession speed of galaxy moving away from the observer is directly proportional to the distance of the galaxy from the observer. Right? In formula form, recession speed of galaxy away from the observer, distance of the galaxy from the observer. H0 is a constant, where V is the galaxy's recession velocity in meter per second. V is the distance between the galaxy and the Earth. H0 is Hubble's constant or rate of expansion of the universe. Okay. Hubble's constant or rate of expansion of the universe. There's a value there, right, given in a data sheet. That's the graph. Right. Key aspect of Hubble's law is that the furthest galaxy appear to be moving away faster. Right. That's an example. Galaxies closer to the Earth are moving away at a slower velocity. More distant galaxies are moving away at faster velocity. Gradient equals to Hubble's constant, H0. Right? Compare equation of straight line. Right? That's what we have just said. Further away a galaxy, the faster its recession velocity. The gradient of the graph of recession velocity against distance is equal to Hubble's constant. Right? Gradient give Hubble's constant. Age of the universe. All parts of the universe is moving away from each other. Right? Remember, the space is expanding. More distant object moving away faster. Matter must have been closer together, very dense on the past. If they are moving away from each other, as we observe today, then they must have start from the beginning. If this is true, the universe likely began as an extremely hot, dense singular point. Hot, dense singular point, which subsequently began to expand very quickly. Right? It's hot, it's dense, so it expands very quickly. The idea is known as Big Bang Theory. Redshift of galaxies and the expansion of the universe are some of the most prominent pieces of evidence to suggest this theory is true. Stop me if you got a question to ask. Data from Hubble's law can be extrapolated back to the point that the universe started expanding. That's the beginning of the universe. Therefore, age of the universe, T naught, is equals to 1 over H naught. 1 over Hubble's constant gives the age of the universe. Current estimate of the age of the universe range from 13 to 14 billion years. There is still some discussion about the age of the universe. Therefore, obtaining accurate measurement for Hubble's constant is a top priority for cosmologists. Right? It doesn't mean that every scientist believe in Big Bang Theory. Right? It still has problems. It has its problem. But in general, most people will tend to accept the Big Bang Theory. Right? Tracing the expansion of the universe back to the beginning of time leads to the idea that the universe began with a Big Bang. Right? Big Bang start, then space expand. No? Try this one. A galaxy is found to be moving away with a speed of 2.1 times 10 to the power 7 meter per second. Galaxy is at a distance of 9.5 times 10 to the power 24 meter from the Earth. Assuming the speed has remained constant, what is the age of the universe in years? Right? Using Hubble's law. Right? H naught is what you want to find. V over D. In a value for V, speed, distance. Get 2.21 times 10 to the power minus 18 per second. And to find the age of the universe, we take 1 over Hubble's constant. Okay, so this calculation gives us about 1.43 times 10 to the power 10 years. Right? Here we got it in second. We convert it to hour by dividing by 3,600. Divide 24 to give days. Divide 365.25 days to give year. Anything that's not clear?
No.
Okay. Okay, so that's all that we have covered for astronomy and cosmology. That's a summarize for you. If you are interested in alternative explanation, creations on Facebook, right? I believe God created universe in 6 days. And then before the global flood, God caused accelerated decay of radioactive isotope. That break the crust. So the start volcanic eruption worldwide. The accelerated decay produce a lot of heat. Right? A lot of produced on the earth and matter in the universe. Due to this decay, to preserve lives on earth, the space was allowed to expand and cool the heated earth. Okay, that's another point of view. This one is past year paper before, I think before 2020 lah. If you are interested in Facebook, you can go to that. Or practical paper 5 before 2020 also posted there. I have not updated it since I retired from Sunday College. If you are interested, you can model answer lah, but on PowerPoint. Okay, page 331, worksheet 25. Let's try some exam question. This is specimen 22A2. A star has a luminosity that is known, right? Luminosity is given. Scientists observe that the star finds that the radiant flux intensity received on Earth of the star, right? There's the radiant flux intensity. Name the term used to describe astronomical object that has a known luminosity. Yep. Yep. What is the term used? Right? Standard candle. Determine the distance. This one you have to memorize the formula lah. Right? That formula, luminosity, radiant flux intensity. That's the distance. You want to find distance, subject the distance. Right? Cross multiply. Take R across there, R square across there, then square root that, and put in your value. Calculate out. Any comment? Anything not clear? Speak a bit louder, cannot hear you.
Okay.
Okay, Sun has a surface temperature of 5,800 Kelvin, wavelength lambda max of light from which the maximum rate of emission occur from the Sun is 500 nanometer. Scientists observe that the star in A finds a wavelength of which the maximum rate of emission occur at 430 nanometer. Usually they try to cover the whole syllabus. That's why they are testing you second part of the syllabus for cosmology and astronomy. Show that the surface temperature of the star, you got 10 more minutes, is approximately 6,700 Kelvin. Explain your reasoning. Right? Use Wien's displacement law. That's all. You need to memorize. Right? There's a star. That's the sun. Right? Take lambda max down. Both are in nanometers, so we are okay. This is the sun. Sun is 500. That's the star, 130. And then surface temperature of the sun. Can
Okay.
use the information in A and B part 1, determine the radius of the star. Right? This is what we have calculated. This is what is given. Right? Go to formula sheet. Get the formula. Luminosity equals to 4 pi r squared sigma e to the power 4. Right? That is radius of the star. Subject R. Right? Take your 4 pi sigma t4 to the other side. Then square root it. Put in your value. Can any comment?
Okay.
State what is meant by luminosity of the star. Total power of radiation emitted by the star. Right? There's the first point you must score. This is taken from 22 February, March, paper 42. Luminosity of the sun. Distance between the earth and the sun is given. Calculate the radiant flux intensity of the sun at Earth. Give your unique answer. Very rare they will ask this one now. Unique because it's started in ES already. Right? Go to memorize the formula. Right? Put in your value. Right? L distance. That's your distance. R squared. That's a 4 pi. Calculate out. Any comment?
No.
Okay. Use your data from B to calculate the mass that is converted into energy for every second in the sun. What should I do? What formula should I use? Yep.
Flux intensity. Wait.
This one tend to use nuclear physics. E equals mc squared.
Okay.
Yeah. E energy divided by time. Right? Time is 1 second. So we want to m over t. C squared, take it down. Right? P is given. P is luminosity. It should be called L. Right? That's a luminosity. And then speed of light square. Okay. So your answer is 4.26 and 10 to the power 9 kilogram. Any comment?
No.
Radius of the sun is 6.693 times 10 to the power 8. Show that the temperature of the surface of the sun is 5770 Kelvin. So they just require to go to the formula sheet, use Stefan-Boltzmann's law, find the radius. R is the radius. Find the temperature of, show that the temperature of the surface of the sun is that. So that's what we are supposed to do. Find the temperature. Right? Root 4, root to the power 4. Put in your value. Right? That's your L. That's your L. Right? 4 pi R. That's your R square. And one get from the formula sheet, sigma. Can?
Yeah.
Right? They try to cover all the syllabus, as I say. The wavelength lambda max of light from which maximum rate of emission occur from the sun is 5 times 10 to the power minus 7 meter. Temperature of surface of the Sirius is 9940 Kelvin. Use the information from D. Right? That's the information from D to determine the wavelength of light for which maximum rate of emission occur in Sirius. That is the formula you are required to memorize. One is for Sirius, one is for the sun. So we want to determine lambda max for Sirius. Rearrange the formula, give T sun down. This is for Sirius. Sorry, C Sirius down. 5570. Lambda max. 5770 from the sun. Okay, out. Okay, anything not clear?
All right.
Sorry, trying to cover for you so that you don't have to stay back another 20 minutes or so. State Wayne's displacement law. Okay, this is from 2022, May, June, paper 41. State Wayne's law. Right? This one should be in your memory work. You should score the point wavelength of maximum intensity is directly proportional to the thermodynamic temperature. Then the next part is figure 10 shows the wavelength distribution for electromagnetic radiation emitted by two stars, star A and star B. Surface temperature of star A is known to be, right, is given 5,800 Kelvin. Determine the surface temperature of B. Right? You are asked to state Wien's law, so they expect you to use Wien's law. Okay. So TB, you want to find, take TA across. Then we do it lambda maximum at A, which is this one, 0.5. Lambda maximum at B, right? Each small square is 0.05. Okay, so this is 0.65. Right? Don't need to convert to both of them same unit, they cancel off. Then 580, 0. Can star B appear less bright than star A? View from Earth. Use figure 10.1 with a reason how this physical appearance of star B compare with that of star A. Any comment before I give you the answer?
Star B lower emission rate.
Why? Right, you get less than 1 minute, so cut off any time. So star B has greater peak or average wavelength, greater peak or average wavelength. Right?
Okay.
Star B looks redder. Right? I think I'll give you all the answer. You can take your time to read there because you cut off any time now. Okay, 22 June, May, June, 42. Okay, all the best to you. We'll see you next Monday.